Hello everyone, welcome to another session of Qoffee Blog. I am your host Akash Kundu and I'm a PhD student at Institute of Theoretical and Applied Informatics in Poland. And today as this guest speaker we have Kanav Setia, who is the co-founder and CEO of QBraid. And before giving an introduction to Kanav Setia, let me give you in a nutshell, let me tell you what QBraid is. It is a cloud-based integrated development environment, which is IDE, for quantum software developers. And Kanav is going to talk about his initiative. And then before Kanav's talk, let me give you an introduction to Kanav. He received his bachelor's in technology BTech in aerospace engineering from Indian Institute of Space Science and Technology in 2011. And then he worked at the semiconductor lab at ISRO from 2011 to 2015. And then he completed his PhD, as it said, from Dartmouth College. And there he worked in quantum computing. And during his PhD, he worked in fermionic quantum simulation and how to increase the efficiency on quantum computers. And at the same time, during his graduation, this program, he was a long-term visitor at the Simon Institute for Theory of Computing. So yeah, we are very much glad to have Kanav here. And Kanav, the stage is all yours, so you can start speaking. Thank you.
Thank you, Akash, for a wonderful introduction. Yeah, super excited to be presenting today. And I just wanted to get a sense of who we have in the audience. Are these people sort of like, have people taken like at least preliminary quantum mechanics, or are they just completely new to the field? So I've actually two different talks and I can present either of them based on the background. So just wanted to get a sense of like what people wanted, like an intro to quantum or intro to quantum simulation. Those are two choices. And let's do a quick voting. Use your Zoom reactions. And for the first one, if you would like intro to quantum, do a thumbs up now. Okay, 1, 2, 3. How about intro to quantum sim 4? Okay, 5. I'm gonna, okay. Okay, I guess it's intro to quantum then. Sounds perfect. Okay, Akash, can you please enable screen sharing?
Yeah, it's done, I think.
Yep.
Perfect. Okay, can you guys see my screen?
Yeah, but it's not a full screen mode. So
Yeah. Slideshow. Stop sharing. Okay, can you all see it in full screen mode now?
yeah, perfect.
Perfect. Okay, so starting off, the story of quantum computation, like before even quantum computation, you need to understand a little bit of quantum mechanics. And the story of quantum mechanics starts with Schrodinger's equation. Before Schrodinger's equation, you had something called classical physics, where the state of the system could be described by only position and momentum of various different particles in the system, right? And if you had that as a given, then you could predict the state of the system in the future, right? And that's where most of your classical physics revolve around. The basic tenet was you had this concept of a particle and then concept of a wave. The concept of particle, and you had those particle comprising bigger systems. You could think of bigger bodies made up of small particles, and then you could describe the motion of bigger bodies. In thermodynamics, you could assume your system to be made of smaller particles, which then you could calculate the velocity, and given the mass and various system entities, you could calculate the temperature, pressure, and so on. So ultimately, everything came down to the notion of particle, and then you had some non-local phenomenon of waves, which and the light. So you had light waves and many other waves. So that was up until 19th century. In 20th century, people started observing a few phenomena which couldn't be explained by these rules. And that's where Schrödinger, first it was Max Planck who tried to explain black body radiation using some different quantity and introducing his Planck's constant. And in doing so, he ended up introducing quantization, which was then used by Einstein to explain photoelectric effect. So, and while doing so, they didn't realize they were introducing quantization for light. Light up until 19th century was thought of as a wave phenomenon. And to come in and introduce quantization was something like an ad hoc thing. And turns out people tried to reconcile these two ideas, where the idea of a particle and idea of a wave, and came up with this wave explanation for even particles. And this is where even the Schrödinger's equation was like a nice culmination to all these ad hoc results, where Schrödinger was like, hey, even the particles have associated with them a wave, and this is a probability wave. And so this was a completely new notion, where you abandon the notion of the position and momentum, and now you were dealing with associating a probability wave with each and every particle and each and every entity in the universe, right? All in all, you have this wave equation, and you have a new theory that describes the microscopic world, or the world at microscopic level, right? Essentially, the big takeaway being the way you used to do physics was changed around 1930, and the rules of the microscopic world are very different compared to the rules that we are familiar with. And I'm going to explain these rules a little bit as we move along. And one of the benefits of quantum computers will be to explain these rules intuitively, or at least give you something to play with where you can understand what these rules are. You may have heard of terms like superposition, entanglement, and some of those things could be hard to understand if you don't have like something that you can play with, a sort of a toy in which you can change the parameters to see if you really understand it. Okay, so far, are there any questions? Remember the big takeaway, you had these position and momentum. Now you are describing the state of the system with wave function. And yeah, that's pretty much it. Okay, there's something in the chat, all clear, perfect. So we're gonna move forward. So at this point, we had new rules. Yeah, new rules given by Schrödinger's equation, and people started to use these new rules to explain things,
Monica, do you
various
have any
systems.
questions? Sorry,
Sorry?
Kanav. Monica, do you have any questions? You unmuted yourself. If not, we can continue. If you have any questions, maybe you could raise your hand using the hand raise option, and then we can call you to avoid noise issues there. Sorry.
You're all
Please
good, all
continue.
good.
Yeah.
Yeah, so now you have new rules, and that's where people started doing various calculations to explain atomic structure, molecules, and so on. And this is where Dirac realized the underlying physics, something fundamental about these laws, where one of the quotes from his paper goes, "The underlying physical laws necessary for the mathematical theory of a large part of physics and the whole of chemistry are thus completely known, and the difficulty is only that the exact application of these laws leads to equations much too complicated to be soluble." Turns out you have your Schrodinger's equation, you try to use it to simulate atoms and molecules. The equations are so complicated that it's really hard to explain or actually do those calculations analytically. And turns out even when people developed digital computers, computationally as well, it remained hard. And this is where the idea of quantum computing was first proposed by Feynman along with, who was it? I forget. There was this another person who also independently proposed the idea in 1980. And Feynman was sometimes very blunt. He said, nature isn't classical, damn it. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. Now, what did he mean by that? He meant, let's say, if you wanted to simulate a quantum mechanical system, then maybe you can make a quantum mechanical system which is controllable. You've got some way to control the various parameters of this quantum mechanical system. Then perhaps what you can do is map this system that you wanted to study to your controllable system and create similar conditions, and you'll be able to understand the system of interest. And at this point, the idea is very vague. A lot of people actually dismissed it. And what he proposed was not a quantum computer, but actually a quantum simulator. And David Deutsch in 1986 took this idea and turned it into a universal quantum computer. So, then what he did was he defined this notion of a two-state system. And I don't think qubit, the term qubit was still defined at this point. What he showed was, one, it was possible to use quantum mechanics to build a new kind of computer. And he showed that that computer could do anything your classical computer was able to do. So essentially, rather than using classical physics to make a computer, you could actually use quantum mechanics to make a new computer that will be able to do all the calculations your classical computer can do efficiently. And by efficiently, what I mean is that the maximum overhead over your classical algorithm will be polynomial in nature. If you don't know what that means, that's okay. Don't have to worry about it. If you have more questions, feel free to ask me. And so that was first result by David Deutsch. The second result was that he came up with an algorithm where you got improvement over classical computer. He showed that with quantum computer, something extra was possible that was beyond the reach of classical computers. And that set the stage for quantum computers that we know today. And most of the field sort of came out of it. Many more algorithms were developed, like Shor's algorithm, Grover's algorithm, and even Feynman's idea of quantum simulation came through. And it seems like we have an exponential improvement over classical computers if we want to do quantum simulation on a quantum computer. Right. So any questions so far? Okay, so up until now, that was a historical overview of quantum computer, and moving forward, I'm going to be um, more thorough in presentation. So I'm going to introduce the concept of a qubit. So what is a qubit? Just like bit, if you don't know like how classical computer works, turns out at the heart of every classical computer is a notion of bit. They make all the CPUs that you know it. The most recent chips in your Apple computers or your phones, they have, I think, more than 10 billion bits that you can control and do operations on. So ultimately, bit is a two-level system that could be in one of the two states, and you represent those states as 0 and 1. Qubit is an analog, quantum mechanical analog of a bit. It is a quantum bit. And just like a bit, it could be in two different states, 0 or 1. But the beautiful part about qubit is it could be 0 and 1 at the same time. And now, what do I mean by 0 and 1 at the same time? So turns out you use wave function to define the state of the qubit. So rather than saying the state of a qubit is 0 or 1, you can actually specify these two complex parameters for specifying the general state of the qubit. And you write the state of a qubit psi as alpha 0 plus beta 1. And what that means is now this is a state that is a superposition of 0 and 1. If you ever wondered what is a superposition, quantum mechanical superposition, then this is it. Like, you define a wave function as alpha 0 plus beta 1. And now you can think of it as it has elements of both the states 0 and 1 at the same time. Now, the question you may have is, okay, I have this weird state that has elements of 0 and elements of 1. What does that mean? When I look at qubit, when I say I look at qubit, I mean I measure it. Would I see both 0 and 1? Turns out, no. When you actually measure a qubit, you will only see 0 or 1. And then you may wonder, okay, if you're going to just see 0 or 1, then how do you know it's 0 and 1 at the same time? Well, it turns out if you do the same measurement, so if you start with a qubit in a given state, psi, as alpha 0 and beta 1, and let's say if I had 1,000 copies, or I prepare the state 1,000 times and measure it, then the state and the measurement distribution would be, I will get 0 modulus of alpha times 1,000 times, and 1 modulus of beta 1,000 times. And so this is where quantum mechanics comes in, where while describing to you how a qubit behaves, I also describe to you a few important axioms of quantum mechanics. One, the state of the system could be present in linear combination of any of the possible states of the system, which means you could have alpha 0 plus beta 1. And let's say if you had another system which allowed for more states, you could have linear superposition of those states as well. And the measurement clause being, when you measure the system, you will only see one of the possibilities with probability modulus alpha square. Oh, sorry, yeah, modulus alpha square. So yeah, as I mentioned, I hope everyone knows what the norm of a complex number is. If not, let me know, I can quickly explain it. And if you're wondering about these weird symbols, these are just denoting your 0 and 1 states. These are called bra and ket. It's called the Dirac notation. But ultimately, you should just think of it as your 0, your 1. And as I told you, when you measure it, the probability of 0 will be modulus alpha square. And of course, the probability of 0 plus probability of 1 must add up to 1. So this is how a qubit behaves. Now, the state of the qubit could be represented on a 3-dimensional sphere. Okay, this is something tricky, and if you'd like, I can go a little bit deep into it. But for the intro to quantum, you can think of it as if you were to represent a general state of a qubit, you do that on a block sphere. You can go through the math because of this one condition that the probability must add up to 1. And you start with a general complex number for alpha, beta, and then you put that condition in, and then you'll see the with the constraint, you're able to represent your state on a block sphere, right? And one important thing is, as I mentioned, when you look at the qubit, you're going to see 0 with certain probability, 1 with certain probability. An important question that you may ask is, how is that different than having a bet and doing a coin flip? And it is very important to know that it's fundamentally different. Probabilities behave rather differently in quantum mechanical world, mostly because they're intertwined with complex amplitudes. And so the way they behave are different. For example, when you flip a coin and it lands and you're not looking at it, then you're not sure that whether it is 0 and 1. And so you can think that, okay, that must be 50% probability 0, 50% probability 1. But you know that it has to be one of those. It cannot be both, right? But whereas in quantum, as you will see, it is actually 0 and 1 at the same time. So in fact, this property was what allowed David Deutsch to do certain tasks faster than a classical computer. So yeah, so that is a very important difference, where when you have a superposition and you do run a circuit on a qubit in superposition, the calculation actually takes place on both 0 and 1 at the same time. And the whole game of actually designing quantum algorithms is to boost the probability of the answer you're looking for. Then similar to what you have in classical computers, you have quantum gates, and these are X, Y, Z, H. Compared to classical computers where a single bit gate, there's only one possibility for a gate for a single bit, and that's the NOT gate. Quantum computers allow for much richer gate set. In fact, there are infinite possibilities for single qubit quantum gates. But a good thing is that with a certain gate set, you can actually reproduce all those infinite gate set using very few gates. So if I give you some set of gates, and then you can use those gates to reproduce any gate that you may want to apply on your single qubit, right? And they're represented just like in classical bits. The wires represent the bits. Here, the wire represents a qubit. A square with a symbol represents a gate. So you've got many gates here. And yeah, and your Hadamard gate is actually a gate that allows you to put a qubit in superposition. And yeah, you have your 0 state that goes to 0 plus 1, and this will give you 50% 0, 50% 1, and then you have 1 going to 0 minus 1 over square root 2. And if you measure even this state, you will get 50% 0, 50% 1, but this phase matters quite a lot. In certain other calculations, this lets you do some interesting stuff. And then you've got your X, which is sort of like a NOT gate. So you've got your 0, which goes to 1, and 1 goes to 0. So if you had a qubit in state 0, you apply 1, you apply X gate, it goes to 1. And with Y, it sort of behaves like the X gate, but it adds a factor of I, which is complex number. And I, for those, I think like, yeah, I don't perhaps need to explain the iota. If you know complex numbers, you know what it is. And then you have Z gate, which if it is in 0 state, it doesn't do anything, but it takes your 1 state and adds a factor of phase of -1. Okay. And then an amazing thing about quantum computer is if you've got multiple qubits, so just the same way you could have superposition of 0 and 1 with 2 qubit state, it allows you to have a superposition of 0, 0, 0, 1, 1, 0, and 1, 1. And if you have 3 qubit, it allows you for 0, 0, 0, 0, 0, 1, and so on up to 1, 1, 1. So it allows, so you're essentially the superposition state of 3 qubits allows you to have elements of all those individual states, all the combinations. And this is where some power of quantum mechanics or quantum computers come from. The fact that you could have a superposition of all the different possibilities, all the different combinations, and then you can do operations on them. It provides you something extra which is not possible in classical computer, and it contributes to the power of quantum computers. So far, do we have any questions? No? Perfect. And so what I'm going to do is maybe introduce C0 gate. So C0 gate is a 2 qubit state or 2 qubit quantum gate. And if you have 2 qubits, what it lets you do is using a control on one of the qubit, it lets you operate on the other qubit. So what it does is if your first qubit, which is, let's say, the control qubit, is in state 0, then it leaves the state of the other qubit alone. But if the state of the first qubit is actually 1, then it flips the state of the other qubit. And both the qubits here could also be in superposition. So you can imagine some really interesting behavior coming up. So if you have superposition of 0 and 1 in the first control qubit, then partially it will flip and partially it won't flip the other qubit. And turns out if the other qubit is also in superposition, you can imagine different combinations. So essentially this is 4x4 matrix that represents, and ultimately each qubit is a two-level system, and each quantum gate could actually be represented by a 2x2 matrix. So if you are thinking of simulating the qubits on quantum on your classical computer, the way you do it is your state of the qubit is represented by a vector. Your gates are 2x2 matrix for single qubit. And if you have multi-qubit system, let's say 2 qubits, then the gates in general will be 4x4 matrix, and the state of the 2 qubits will be a vector of dimension 4. Okay, I may be going into too much depth, but so far, do we have any questions? I'm going to look in the chat. It's kind of oh, thank you for taking Yuri Manin. Yeah, thank you, Ritra. Yuri Manin was the second person along with Feynman who came up with the idea. And thank you, Ritra, for answering Jessica's question. And yeah, so you've got your 2-qubit gates, and then based on these gates, single qubit gates, 2-qubit gates, you can build your algorithm and do certain tasks faster than classical computers, right? And as I mentioned, these are different. So going from C0, you can also have a control X, which is just C0, and then you can also do control Y. So essentially here the concept is if you've got if you've got a qubit, you can have it as control, and if it is in 0 state, you leave the other qubit alone. If it is in 1, then here you apply Y gate, Z gate, H gate, and even any random unitary. Okay. Let's see. Yeah, as I mentioned, you've got your universal quantum gate set. So this is the gate set that allows you to generate any random unitary or any single qubit quantum gate. Okay. I think this is where I want to maybe stop and give you an introduction to how to program these things and where you can go from my talk. So can you guys still see my screen? Or perfect.
Now we do.
Okay, now you can, right? So essentially, what I gave you was a little bit an overview of quantum computers, quantum computing, and a little bit about QBraid. What we do is we provide you a place where you can go learn this skill set and even develop your own quantum software that you can share with others. It's free to join. You can make an account with only email and password. Once you're in, you will see 2 different sub-platforms. One is called Learn, the other one's Lab. The Learn platform is where you can continue your journey that you started today in quantum computing. You just launched this course, and this is where we have a very basic course, and all you need for this course is just complex numbers. We don't even require linear algebra. So turns out Andrea Coladangelo, who did video lectures, was of the opinion that there should be a way to even leave out linear algebra. So even the details that I presented today were a little bit extra. For this course, you don't even need that. And here, the best part is a lot of interactive videos, how waves superpose. You can play with a lot of the widgets. And you can actually get started with programming quantum computers. And to give you a brief introduction to how you actually program, if you are familiar with Python, then it'll be relatively simple. You just import a quantum circuit object from Qiskit. You initialize the quantum circuit, and 1 here, 1, 1 here represents 1 classical bit and 1 qubit in your quantum circuit. And the gate I presented, the Hadamard gate, is just H gate. And then you say measure the qubit, and you can draw your circuit. So first, let's just run it. So you can click play and the circuit runs. So it prints out your circuit. Here, you were applying just Hadamard gate to your qubit, and then you measured the qubit. So you measure the qubit, and then it shows up on your classical bit. What you can also do is you can add more gates like X gate 0, and then you can do dot Y gate 0, cert dot C gate 0, and then you run it again, and you can see a bunch of circuits show up. So programming quantum computers actually is not that hard. Once you understand the circuit that needs to be built, it's relatively easy to build those circuits and play with them on a real quantum computer as well. And then let's say you build your circuit, you want to simulate that circuit in your computer. Let's say you don't have access to quantum computer. Then what you do is you import air and execute, which is a package that allows you to simulate your quantum circuit. And if you remember, I told you if you've got a circuit and you measure it, and if your qubit was in superposition, you will get a distribution. So which is why most quantum circuits, you run it 1,000 times, 500 times, or however many times you need to get a distribution to understand what the state of the qubit was. So let's say if I run it, and you'll see that my distribution was, I got 0, 508 times, 1, 516 times, right? So if I remove the Hadamard gate, I have X gate alone, and I run it, and now initially the qubit was in 0 state. I flip it and I run it again, and I see that 1 shows up 1,024 times, which is exactly the number that I ran it for. So what does that mean? That means that there's no superposition in the system, and qubit is in perfect 1 state, right? So, which is where you now kind of understand that Hadamard gate allows me to create a superposition, and then I can run it, and you can see if I keep running it, the distribution keeps changing. And if I increase it to 2,000, it'll take a little longer, but now the distribution comes very close to 50%, right? You can also plot this. Another cool thing you can do is you can do 2,2, Hadamard, you can do C0, I think, and then 1,2. Let's see if it runs. Oops, your indices start at 1, 0, 0 and 1. And you can do other cool stuff here. X1. You can also do cert dot H1. Right. So you can play along. And then you can do cert, and I just have 0, 1 and 0, 0. So now the 2 different options that I have are 0, 0 and 0, 1. If I want to do something exciting, I can just change it again to, let's say, 0. And then what do I want to do extra? Cert dot X 0 as well. Let's see if that does anything. Then, yeah, I still have 0, 0. Let me apply a Z gate here. 0. Let's see. And then, am I flipping it? That is very interesting. How about how if I do this? That is very interesting. I have both the Hadamard gates here, and I'm not getting the other, maybe I'm doing something wrong. But anyway, takeaway from here is that it's actually relatively simple to play with these things. And we've got an entire course built for you where we take you to from like some really exciting stuff like Deutsch's algorithm, a couple of other non-local games and entanglement. And once you're ready, you can actually move on to our lab platform where you will get access to software from all the different places, IBM Qiskit, Xanadu's Penny and you can install any of these things. With Amazon Bracket, we actually now even support hardware access. So let's say you want to actually credits to connect to IonQ's quantum computer, D-Wave's quantum computer, and a few others. Then yeah, just reach out. We'll be happy to provide you hardware access as well. And all you have to do is go here, click activate. Oops, I just have to refresh. And then you just activate your environment and then run a single command, QBraid enable account AWS_bracket. And after that, after you run that line, you'll be able to run any circuit on IonQs, Rigetti's, or any of the quantum computers that you like. But you will need an access key that I'll be happy to share. You will go in and put in the access key on account page. I can show you. The best part would be you'll be able to just open any of the notebooks available from AWS. So when you make an account with us, you'll see QBraid tutorials in your home directory. Just open that, go to tutorials, AWS tutorials, and let's say getting started and running, preparing GHZ state. Make sure to select bracket environment, which you will need to by going here, clicking activate. Once you have this activated, you will be able to select bracket, and then you'll be able to run various programs. And the best part is you don't need to do any configuration. So Amazon Bracket, your bucket name, just leave it alone, and you'll be able to connect to real hardware or run simulation. So this would be a GHZ state. You can print the circuit, and then you've got your local simulator working. That goes through. Let's see if there's an example here. So, and then you have state vector simulator available through Amazon in the cloud. You can use that as well. Let's see if I have any real devices. No, I do not. I think it was a different notebook. Selecting bracket, select, and oops, circuit is not defined. Runs. Okay, do I have? Yes. So there you go. This is the example where, so this is the line you would need to run. QBraid enable account, AWS bracket. And if you run this line, you'll be able to submit jobs to real quantum computers. Whoops, something's off. I think I have outdated, outdated ARN for the device. But if you put that in, you'll be able to connect it and submit jobs. Right. Any questions so far?
So no, there was a discussion on, so Q World has Q Bronze and Silver, and it's something like the courses that you had mentioned.
Okay.
The aim is to use Jupyter notebooks to take people from very basic introductory level to somewhere being able to understand Grover's algorithm, Shor's algorithm, the likes. And Anuj and Tamal was suggesting that since they also use Jupyter notebooks, maybe it's interesting to figure out if the QBraid platform will support this. But
Yeah,
maybe
yeah, yeah.
that's, yeah.
I think that's a wonderful suggestion. We'll be happy to work with you to like port. So here's really cool thing that we do for a few other organizations. So if you've heard of Unitary Hack,
Yeah.
got their environment available here. If you activate this, then you'll be able to use Metric and Metig without having to install a single thing.
Right.
Right. And maybe we can have another Q world here so that every package that people need, it'll
Right.
come pre-installed and they wouldn't have to deal with installation procedures and so on.
I see. That's interesting. So whom do we contact to talk about this? Do we
Yeah,
speak to you
you
or
can just drop me a line and I can forward it to Ryan or Ricky on our team and they can make it happen very soon.
perfect? Yeah, we'll do that after talking to people from Q World also, just to, yeah.
Other cool thing, as I mentioned, we do also give out credits to connect to hardware. In fact, we supported the QC hack, the hackathon by Stanford and Yale.
Right.
And that's where we gave out. So if anyone's interested in exploring access to real quantum computers through IonQ, D-Wave, Rigetti, yeah, we got you covered there as well.
That'd be awesome, especially if there are any PhD students listening and maybe.
Yeah, that's pretty awesome. I agree.
Yeah.
Yeah. So we already have, as I mentioned, connections to these, but we are also working with a few other hardware vendors. Hopefully IBM Access should be coming soon as well, and a few other companies as well. So
Right.
yeah, this year should be exciting. Later half of this year, you'll see many new quantum computers pop up. And best part would be no configuration required. You just do QBraid enable account, AWS. You've got all your quantum computers available through AWS,
Right.
and it'll be similar for other companies as well.
Awesome. Awesome.
So I kind of saw Pascal's logo there. So can you also program neutral atoms the way that we do in normal compute?
So Pascal, good catch, Aritra. So all we do is we provide access to their SDK called Pulsar. We are working with them. We've had like a few conversations with them. In the future, there's a chance that you'll be able to access their quantum computer as well. So if the talks go well, if they are excited, they were very excited to provide Pulsar access through QBraid. So yeah, you can use a Pulsar, which is their SDK, without having to do any installation. I don't think we put their Pulsar tutorials in QBraid tutorials, but in the coming months, that'll happen as well. So when you make an account, you'll see Pulsar notebooks popping up in your home directory as well.
One more question. Like this seems like a super good platform for benchmarking the different like hardware platforms. So is anybody like doing it, not from QBraid, but any other researcher who is doing that as like using this platform for benchmarking different hardware?
There are few. No, I shouldn't, like, I know a few people are working on it. Like internally, we try to do that as well. But if you want to do it, we'll be happy to provide you a few credits that you can use for various things. And then one good thing another really cool thing that we're working on is, so we really want to provide people the ability to share their work with other people. So essentially, oops, let's say you build a notebook and it's an explanation to connect to various quantum computers, and you've built your circuits. You'll be able to publish your notebook as a blog. So this feature doesn't work right now, but it should be up in coming weeks. And then when you publish that blog, it'll show up on the account page. So when people go here and check out the blog section, and your blog will be here, but the best part is when people are reading your blog, not only will they be able to read whatever you published, the notebook, but they'll be able to play with the code you published as well. And that'll be like an industry first feature. So for example, this is a blog by ex-QBraid employee named Graham Jacobson. So he published this like an example, an explanation of B92. But as you can see, this is like the same notebook that I showed you for QBraid Learn. So all the code, people will be able to press play and it runs, right? And yeah, so when you do a benchmarking study and you want to publish it, yeah, that'll be another really cool feature that you can use to share with your network so that they can actually just come in. They don't have to do any setup. They'll be able to use your code.
That's super cool. Like the blog plus platform thing is already, I think they're in Strangeworks, but they don't have this online playing around with the blog post as well. That's nice. That's
Yeah, yeah. So some more really cool features coming soon as well. Blog is one of those. Another thing we published that may be of interest to you guys as well. So we also released QBraid SDK, which allows you to transpile your circuits from Qiskit to Circ to Bracket and so on. In fact, the winning entry at QC Hack by Stanford and Yale, they use QBraid SDK to run, to build their actually circuits in Qiskit, then ultimately run on Rigetti's hardware by transpiling it using QBraid SDK, and then running it on SDK, Rigetti's quantum computer and IonQ's quantum computer through Bracket. And yeah, we're going to keep developing QBraid SDK. Hopefully some VQE related features will be coming up in the next 6 months or so.
Akash would be very happy with that.
Yeah, I would be very happy. Yeah.
Right. So Kanav, there was a question by Jessica in the chat. So maybe
Okay. We can continue to.
So it's the second last chat. So maybe go.
How could we work towards QC open source as undergraduates? That's a great question. I think there's not a single strategy here. I would say depends on what exactly you want to accomplish. Even if you don't want to contribute directly to QC, there's still like requirements within open source platforms for other things, right? There's going to be many issues open. So I would say go to Unitary Hack, look for the issues. And sometimes these issues could just be pure Pythonic in nature. So while you are building your quantum computing skill set, those are easy things you can fix, right? Contributing directly to QC could be sometimes hard because it's steep learning curve, and figuring out how you can fit in and contribute effectively could be hard. But while you're figuring that out, there's still always possibility to just contribute, and people are very happy when you do that, and they'll make your experience with other QC projects much better.
Also, writing these blog posts and having tutorials explaining different concepts, although you're not exactly maybe adding a new feature to the code could be a good way to put yourself out there, right? And
Yeah, that's perfect actually. While you're learning, help out others. The best way to
exactly. Yeah.
make sure that you learned effectively is just to explain to other people, write a blog post.
So you talked about this individuals going into the QBraid platform as well as like unitary hack, but you were also working with some universities in the US, right? Where they
Yep.
use this platform, and so how's that going, or how did that go?
Yeah, so essentially, QBraid is incredibly easy to use even for professors, because if you, I'm sure you've had experience with quantum software, and beyond quantum software, there's just like a lot of extra Pythonic stuff. So if you are in your junior year, in senior year, and you've been following physics track, then you may not know very well how to program. Then coming into a quantum computation, quantum software course, you'll have to learn first the quantum computing basics, and then fiddle around with Python. Install Python, install Qiskit or other packages, then Jupyter, and there's like a high probability of making an error. So if you're teaching class with 100 undergrad students, it gets incredibly hard as a professor to, because somebody's going to have a Windows outdated version, a Mac, again, some weird version, somebody's Linux. And so they don't want to be the sysadmin. So this is where professors find it incredibly simple just to tell students, hey, sign up on QBraid, use this particular environment, here's your assignment, and they share Jupyter notebooks. And there's a bunch of code that they can run to test out it runs, and then they have your code goes here that students can program.
So like the university that you are currently working with are all in the US or also in India or Europe or somewhere else?
Mostly in the US, but we're super happy to work with other places as well. We actually did a hackathon with New York University in Abu Dhabi. So there's a good chance they'll be continuing with QBraid as well. Yeah, so far it's mostly been US and Canada. But we're always expanding. If you've got need, if you're teaching Erythra, if you're a TA, feel free to reach out. We'll be super happy to work with you, create maybe a specific environment. In the coming weeks, you'll also see another feature popping up, new environment, where you'll be able to create your own Python environment, install a bunch of stuff, and then you can just share that environment with your collaborators or your entire class. Okay, so that once you have your programs working, bunch of stuff installed, you just share that exact environment with everyone you want, and they'll just get it. And so not only they'll have reproducible code, but reproducible runtime environment. And that's essentially our goal.
That's pretty cool. And maybe we should, so we know that NPTEL has this quantum computing course, right? Maybe people are interested.
Oh, nice.
Check that out. Okay, nice. So that's a couple of different threads to follow.
Yeah.
Thanks, Kanav.
We do run a few quantum computing camps, and we do get a lot of interest from India, but we haven't been able to get in touch with professors teaching courses there who want to use our platform. But super open to it. Like we'll be super happy to even provide access to quantum computers as well.
Right. That's actually very interesting.
Yeah.
I think that'd be really cool too. Thanks, Arthur. Bring that up. And maybe if nobody else has any questions, could you briefly mention about your startup journey, how you went from being a PhD academic person to being a founder?
It has been a long journey. Like I've already been doing it for more than 2 years now. Yeah, it's 2022, right? Yeah,
Yeah.
think somewhere around third year, I thought, hey, wouldn't it be cool if I get to do a startup? And it's an iterative process. Like we're still learning. The market is super early, and so finding a product market fit has been hard. We're just starting to see where a lot of people getting interested in our platform, and essentially it for me it ended up being like another PhD, to be honest. You know, like how you get into PhD and the first 2 or 3 years are super rough and you're like, oh, I don't know what I'm doing. Like, am I ever gonna get a paper? And then like yeah, it's a very different version of that, but it's the same amount of grind where you're like always working and trying to figure out things. And it's, I think, a little bit harder than PhD, to be honest, because there's so many different skill sets you have to just pick up. And the legal aspect, and then like hiring people, a bunch of new software, speaking the lingo of investors, and trying to sell products. And so there's just like all the different things that you didn't even know that these skill sets existed. You kind of have to just pick up and do them. So it's like incredibly exciting journey.
Right. Yeah. Awesome. Awesome. Great. And
Yeah.
maybe, yeah, do you know of any internship opportunities at QBraid? I'm sure there'll be people interested.
Yeah, if any of you are interested, definitely send us a resume. Mostly for us, I think we don't have to. We fortunately we never have had to publicize
Right.
internship opportunities too much. Since I think last year, after our platform started to get used at various hackathons, we generally get a couple of people reaching out. Hey, this looks incredibly slick. Do you have an internship opportunity?
Right.
So we just hire from that. So mostly, like, if you're interested, you've got a good use case, good idea where you would like to fit in on the classical side or on the quantum side, definitely drop me a resume, or just send your resume at careers@qbraid.com, and just like provide a little blurb what you would want to work on, and we can reach out.
Awesome. And you would like to be contacted on LinkedIn? Maybe drop
I
your
think
email.
I think we are a small team.
Right.
We are trying to hire a few people moving forward. The second year, the second half of this year is going to be focused on enterprise. We are very close to closing one big contract, and we raised some money earlier this year. We're trying to raise more money. So essentially, we'll be growing fast in the second half of this year. So
Awesome.
yeah, if you're interested, definitely reach out. We'll have projects on the research side. Classical software is where we would love people who know, honestly, JavaScript, Python. Yeah, if you know JavaScript, React, and those sort of things,
Perfect.
that would be great, to be honest.
So that's the final question from me. Have you also considered working with bachelor thesis with students, or do you already do that? I mean, you mentioned that you're working with courses, I mean, with professors to support their courses and so on, but
Yeah,
bachelor thesis
absolutely.
maybe, yeah.
Last year, one of our, a few of our incredible interns were like freshmen,
Right.
sophomore. Ultimately, a few people start really early, and at most places there aren't any quantum courses available.
Mhm.
So, but there's so much online material.
Mhm.
So if you are smart, you've spent enough time learning the skill sets, then yeah, we don't care whether you're bachelor, PhD, or
Exactly, yeah. So for all the students listening, this could be a good opportunity.
Yeah.
Definitely hit Kanav up. Or yeah. Okay, yeah. So I'm done with my questions, and this was really, I think, a very good presentation. Akash, do you have any?
Yeah, I mean, I don't have any questions, but like you said, like you're going to deal with the creational algorithms next. So for me personally, it is quite exciting, and I think it is going to attract more researchers, also students. Like yeah.
Yeah. So that's what our goal has been, but it gets tricky. Like creating a high-level algorithm like variational quantum eigensolver (VQE), coding it up, and then making sure it works with Bracket, IBM, and a few others. That's like incredible challenge because there's just like layers after layers in each. So I'm not sure if you've gone deep into Qiskit, but you start out at quantum circuits, then you've got quantum data structures, then you come to algorithms layer. And in the algorithms layer, VQE has a bunch of different components. There's optimizers and so on. And making the same infrastructure work for all the different quantum hardware. Yeah, so that's where our most, it has taken us a decent amount of time, but that's where we're going. Ultimately, we want to provide you the ability where you just define your VQE and we'll manage access to different quantum computers.
So I have like this question. You say like if somebody wants to work in QBraid or something, so they will just send their CV and maybe their proposal. So right now we understood that you are proceeding towards this variational algorithm, so people can come up with some idea related to that and for the future. But right now, which kind of project you expect, like from the applicants or like students or something, like Rishi said, like for bachelor students, or if they want to do some internship or like thesis.
Thesis, I think it depends. As a bachelor student, where you've spent your time. For example, a few people have already who reach out, they've done some work already in either quantum machine learning, VQE. So that's where we at least know, okay, maybe like a couple of software development packages, how to build circuits, and then matrices, your linear algebra well. Once you have these skill sets, then we can together work on a good project with you, right? So that's where we generally propose. Many of the projects moving forward will be dictated by our clients. So if they're interested in specific problems, we will generally share that problem with you, and we'll work with you to come up with a solution to address the problem, right? And yeah, that'll be the strategy where we'll identify this is the problem that we want to solve, and then what is the best algorithm, and then we'll work with the intern so that they can build the required circuits, do all the simulations, and so on.
Yeah, thanks for the answer.
Yeah, hi, Kanav. This is Anuj here. Can I ask a question?
Yeah, go ahead.
Thanks. So just want to know, like you might have seen that if I mainly talk about the research area, mainly the people who were there who were using supercomputer or the high performing computing platform, they are the ones who are actually moving and opting, or I would say testing the quantum computing environment. And there is also an approach where there are certain actually organizations you might be also aware of, which are trying to integrate the quantum computing environment with the HPC environment. So are you planning to actually have a environment, set up a sort of actually a runtime sort of thing within QBraid itself? Because I think people who are, it will be a staging platform for those who are actually trying to move or integrate their workload with like HPC plus QPU type of thing.
That's a great question, Anush. Thank you for that. The answer is yes. So our goal as a company moving forward is to provide people the simplest access to scalable classical as well as quantum compute. So you'll see moving forward, you'll have environments and different computes popping up. So you'll be able to swap out the machine that is powering your Jupyter instance with much bigger machine. Let's say you say, oh, I want to do 30 qubit simulation with a specific simulator I wrote, then we will provide you that. You'll be able to choose a bigger instance, and you'll be able to choose a bigger instance along with GPU support.
So, sorry, follow-up question is agnostic. Agnostic. There is an organization you might be aware. I think a Canadian like organization.
Yeah.
So, are you considering them also? Because I think they provide these type of solutions. Agnostic.
I have heard of them for sure, but I don't.
There are many. They work in finance domain, and they are also working. They already have a API which actually already takes care of the integration part, and I think they are also working on the neutral atom computing qubits also.
Yeah, I think that's where we think API access is not difficult. Like, in fact, writing an API for us.
It is a SDK. Yeah, they have a SDK actually. They already have a SDK which integrates and takes care of different, not only from one organization, but they can select like it is a sort of a front end for many different actually cloud platforms as well as across the GPUs as well. So might be like if that could be actually introduced as a test version, or because you guys are actually there already in North America, might be easy. And I think the technology person who is actually there, he is of Indian origin. So might be of help to you.
I honestly, Anuj, like, I haven't seen detailed description of their product. So if you can share where you found this information, that'll be really helpful.
I'll share that.
Yeah, that sounds great. Yeah, ultimately, as I mentioned, we're also moving in that direction as well. But our strategy always has been everything available from the development environment that most people are already familiar with. So just the same way I showed you an environment extension, you will see another extension popping up that'll control your compute resources. So just the same way you click activate and you move to a different environment, you'll have different machines listed in this new extension, and you'll just click that I want to use this machine, and we'll swap out the backend for you.
Awesome. If there aren't any, are there any more questions for Kanav?
Cool.
I don't think there are any questions, but there are some resources shared on this chat. So I'm going to post them on the Discord.
Perfect.
Yeah. So if there are no questions, please.
QBraid also has a Discord server, right? So I think you can find the link to that on the QBraid website. So if anybody's interested, check that out also.
Yeah,
that would be very nice. Yeah.
Awesome. Yeah, thanks, Kanav. This is very productive, and
very productive. Yes.
Got of new leads. We'll be writing to you soon about that.
I'm very happy that you guys all liked it. Yeah, always feel free to just reach out. Happy to work with you all. And I really believe that the first step in making this field a reality is to have more people coming to the field. So
exactly.
Incredibly excited to support all of your endeavors, and encourage your peers as well, bring more people into the field.
And yeah, that's what QBraid is trying to do.
All right. Thank you very much.
Yeah.
Bye.
Take care. See you.
Yeah. So thank you very much for joining again. Kanav, it was very nice. And take care, everyone. And until the next session.
Yeah.
So see you. Bye.
See you all. Bye. Thanks for joining.
See you. Bye. Bye, everyone.